Another recitation video. This week we're going to be talking a lot about NMR, so I'm going to go ahead and jump right into it. So a quick reminder, NMR is nuclear magnetic resonance. So when we're looking at NMR, we're going to be looking at changes in the spin states of nuclei at the low end of the energy spectrum. And remember that those are longer wavelengths. So we have shorter frequencies, longer wavelength. And we can use this to solve structures in a solution phase. So looking a little bit about what spin state of nuclei actually mean. So nuclei have a magnetic moment, and that is based on the protons that are in the nuclei. So the protons are like a spinning charge, so they generate a magnetic field, kind of like what we see in that image right there. So you can see the magnetic field is formed, and basically we have that that magnetic moment that happens. Then we can apply a magnetic field to that protein, and we can see whether or not it lines up with that magnetic moment or if it opposes it. And that's so if we look at a graph of what's going on, we have our magnetic strength down here, and then we have the energy of the system up here. So the difference that we see here is how much energy is needed in order for that specific magnetic component to cause the energy change. So we're trying to go from a plus state to a minus state, so we're going to see this jump in energy based on the magnetic strength that we apply to the system. And when we look at the equation that we actually have that the energy is equal to H gamma times B over 2 pi, which again is also related to HF. So remember that B is the magnetic field strength, gamma is the gyromagnetic ratio, which is the ratio between momentum of spin to magnetic moment. And that is going to be different for every atom. So make sure that you don't try to use the same thing for different atom types. Okay, so remember that NMR is not a sensitive technique. So remember again, when we think back to some stuff that we did previously, that N upper and over N lower is going to be this equation right over here, where we get E raised to the negative delta E over kBt. And we look at the different E values that we have. So for short wavelengths, such as X-ray, that's going to be some pretty high energy. So we're going to get some pretty distinct patterning between the low and the high. And then if we look at something like NMR, which has long wavelength, we're going to have a smaller E, and therefore it's going to be a ratio that's pretty close to 1. So the next thing I wanted to talk about is resonance. And resonance is when a protein is in a lower spin state and can absorb energy and flip to a higher spin state. So when this happens, the nucleus is said to be in resonance, and that is after a magnetic field has been applied to it. So as we can see in this picture up here, we have a nucleus that is in the spin up position, and after it absorbs some energy, it's going to come to this higher transition state, and that means that it's in resonance. So when you're looking at NMR in an experimental setting, basically you're going to hit a sample with a short pulse that contains a range of frequencies, and that's going to cause the nuclei to flip the state that it's in. And then when it relaxes down again, the NMR machine detects the energy given off, and it is able to determine what the shift is. And remember that shift is the frequency observed minus the reference frequency divided by the reference frequency times 10 to the 6th. Because we look at stuff in parts per million, so that's where the 6th comes from. So when we're looking at this graph down here, we have our NMR data, and remember that the more to the right that we are, the more shielding that we're going to have. So that means that the nuclei are more protected and the electrons are not going to change as much. And then as we move farther down field to the left, we're going to increase our frequency, and that means we're going to increase our energy. So some things that can influence the observed frequency are the type of atom that you have, the environment or the shielding that happens, and some specific things with that is how much the nucleus is protected or exposed to the magnetic field. So if you have something that has an extreme electron withdrawing group, it's going to be more exposed, and therefore it might be shifted down farther. And then where the atom is related to other atoms. So if you have something that is in a protein backbone versus an aromatic ring, you're going to get severely different NMR data from that. So remember that the higher the electron density around the nucleus, the higher the opposing magnetic field, the greater the shielding, so lower frequency required to achieve resonance, so it's going to be a smaller shift. I know that's a lot of words, but it helps relate everything back together. Okay, a quick example of how you can actually use this stuff. So if you have a 400 megahertz NMR instrument and you get hydrogen shifts of 1 parts per million and 2 parts per million, what are the observed frequencies? So we can take our delta, which is the 1 parts per million and 2 parts per million, and we have our reference frequency, which is the 400 megahertz. And basically what we can do is pull out the megahertz part because that's accounted for in the 10 to the 6th, and do our F obs minus 400 divided by 400, and we get that our shift is 400 hertz for 1 parts per million and 800 hertz for 2 parts per million. So that's what I got for you guys this week. Hopefully that makes some sense and helps you figure out how you can use NMR for your studies.